anyhow, so it's about 5 after now, so figure I'll go ahead and start the lecture. Looks like we've got 3 people online. Today I figured we'll just go over a bunch of problems from the homework for the first half and then get into a little bit of chapter 5. Having said that, I do want to let everyone know the third exam will be next week. It will cover all of chapter 4 up to 5.3. And if I remember correctly, 5.3 is it's overuse sub and integration, particularly with like the Elling. Having said that, we pull some of these examples off the homework really quick. So I don't think we need help sketching any of the graphs. I think that's pretty straightforward.
I had a question on it was 12 and 13. It was find the derivative of exponents.
The derivative of exponents, okay?
Going through a few of those, I guess.
Which homework was it?
12 and
Part 1 or part 2?
part 1.
Part 1, okay.
Yeah.
Okay, so I wish I had this hooked up to the projector, but unfortunately I don't. All right, 12. EX squared plus 8. You just want to find the first derivative of it, is that correct? Yeah. Oh, it's plus 8 in the derivative, the exponent, okay. All right, so looking at number 12 from week 9, part 1 homework, we're given a question that looks something like this. For some of y'all, this constant here, the single term may have changed, maybe like 10 or something else, but generally this is what the problem looks like, and it wants us to find the derivative of this thing. Well, we know from the general rules of exponents that the derivative of e raised to some function of x is going to be equal to e raised to that function of x times the derivative of that function of x. So when we find the derivative of this thing, it's going to be helpful to note that here, x squared plus 8 is playing the role of u. So when we take the derivative of e raised to the x squared plus 8, this thing's going to come out to be e times, or e raised to x squared plus 8 times the derivative of that exponent so altogether, our derivative is going to evaluate out to be 2x times e raised to the x squared plus 8. You said was the other one?
Yeah. think I made the mistake of not putting the parentheses in between 2x and e.
That will happen.
That's probably what I don't.
All right, so for 13, we've got something that's a little bit more involved. I can work with this. Yes, I can. Dope. All right. Is equal to x squared e to the x minus 2x e to the x plus 8 e to the x. All right, so we want to find the derivative of this thing. Well, we know from properties of the derivative that we can just evaluate the derivative on each of these terms individually, right? So the derivative of our function is going to be equal to the derivative of the first term minus the derivative on the second term plus the derivative on the third term. Notice here and here, we're going to have to use the product rule. And the product rule told us that if we have the derivative of two functions, let's say g of x times h of x, this is going to come out to be h of x times the derivative of g of x plus g of x times the derivative of h of x. So when we go to derive or to calculate these derivatives, we're going to find that this comes out to be the derivative of x squared. It's going to be 2x times e to the x plus x squared times the derivative of e to the x. But the derivative of e to the x is just x squared. I mean, it's just e to the x, sorry. Minus this thing, we can pull out the constant. The derivative of x is just 1 times e to the x is e to the x plus x times the derivative of e to the x, which is just e to the x, plus the derivative of 8 times e to the x. We can pull out the 8. The derivative of e to the x is just e to the x. Now we have some simplifications that we can do. We can pull out e to the x. When we do, we're going to get 2x plus x squared minus 2 times 1 plus x plus 8. And finally, we can simplify this even further. wherever it goes, oh, right there. When we simplify it even further, we get e to the x. We can drop all these parentheses and distribute this 2 through, right? So we're going to get 2x plus x squared minus 2 minus 2x plus 8, or e to the x. These two 2x's are going to cancel each other out. So we're going to be left with x squared. 8 minus 2 is just 6. All right, what's another good problem? Let's find 14 as well. All right, so looking at the next problem. The next problem is e to the 2x minus 4, that quantity squared. We want to find the tangent line at 0, 9. So first question, does this in fact evaluate out to be 9 when x is equal to 0? And it does in fact. So that's cool. We've got that right. The next thing we need to know is that the tangent line is going to be of the form y minus 9 is equal to the derivative of our function, which I'm just going to write as m for right now, times x minus 0. So we're going to have to find the derivative of our function. F prime of x is going to be equal to the derivative of e to x minus 4, this quantity squared. Well, we can apply the chain rule here. Take the derivative of the outside, leaving the inside intact, times the derivative of the inside, right? So this is going to come out to be 2 times e to the 2x minus 4. All that times the derivative of the inside, which is just going to be 2 e to the 2x. So now we need to evaluate our derivative when x is equal to 0. That's going to come out to be 2 times e to the 2 times 0 minus 4 times 2 e to the 2 times 0 so this will evaluate out to be 2 times negative 3 times 2 or 4 times negative 3 is negative 12. So now we're going to go back to the line or the equation for our tangent line and start solving things. We got y minus 9 is equal to negative 12x solving for y, we get negative 12x plus 9. Let's find another problem now. All right, let's look at 15. That's another good one. Oh, my mistake. So this was problem 14 for whoever's watching, right? Sorry about that. Now this next problem, like I said, is going to be problem 15. And what we're given is x squared times y minus e to the y is equal to 0. And we want to find dy dx. So we're going to have to apply implicit differentiation here. Taking the derivative of both sides, d dx of x squared y minus e to the y is equal to, well, the derivative of 0 is going to be 0. This is going to give us d dx of each individual term, right? So we're going to have to apply the product rule here. And when we do, we're going to get 2x times y plus x squared times dy dx minus the derivative of this thing under implicit differentiation is going to come out to be e to the y times dy dx Now, why is that? That happens because we can think of this y as a function of x, right? So using the chain rule, we're gonna get dy dx left over. Make sense what I mean? Now all of this is equal to 0. Rewriting all of it, we've got 2xy plus x squared dy dx minus e to the y dy dx is equal to 0. The first thing I would do is subtract our 2xy from both sides and factor out the dy dx from these two other terms. So we're going to get x squared minus e to the y times dy dx is equal to negative 2xy now we're just going to divide both sides by this x squared minus e to the y. Ooh. Time for bed. And that's it. That's all she wrote for 15. Oh, they had an extra term in there that I didn't catch. That's all right. All right. What's another good problem? This is a good one. All right. For this next example, we're looking at number 25. We want to simplify 1 over 3 times 6 times the ln of x plus 6 plus the ln of x minus the ln of x squared minus 1 . So we want to simplify this thing. The very first thing I would do is pull this 6 inside using that power rule that we have about logarithms. So that would look like this now, 1 over 3, the ln of the quantity x plus 6 raised to the 6th power plus the ln of x minus the ln of x squared minus 1 Now, I would use the product rule of logarithms to combine these two terms to get 1/3 times the ln of x times x plus 6 raised to the 6th minus the ln of x squared minus 1 . I forgot to close that bracket. And now, using the division property of logarithms, I would combine these two terms to get 1/3 the ln of, this is going to be a giant beast, x plus 6 raised to the 6th divided by x squared minus 1. And now again, using the power rule, we're going to get the ln of x times x plus 6, all of this raised to the 6th divided by x squared minus 1. All of this raised to the 1/3. We can simplify this even further by distributing this 1/3 all the way through. And when we do, we're going to find that this comes out to be the ln of x to the 1/3 times x plus 6 squared divided by x squared minus 1 to the 1/3 power. And that's it. It is as simplified as we're going to get it. At least insofar as what I see. We might be able to do some more simplification inside, but this is where we're going to stop for right now with this problem. All right. Let's look to see if there's another decent problem here. Yeah, 26. That's a good one. All right, so for 26, we've got e to the ln of x squared, that quantity minus 4 is equal to 0. What's x? So the first thing I would do is take advantage of the logarithm power properties and add 4 to both sides. So this is going to look like e to the 2 ln of x is equal to 4. So all I've done here is added 4 to both sides and used that power property of logarithms. Now, we're gonna take the logarithm of both sides. But notice the left-hand side, this is just gonna come out to be 2 times the ln of x. So now we're going to divide both sides by 2 to find that the ln of x is equal to the ln of 4 divided by 2. Now we're going to raise both sides, or e, to both sides. So what I meant to say is we're going to say e raised to the ln of x is equal to e raised to the ln of 4 over 2 . So now, this is going to come out to be x is equal to e raised to the ln of 4 over 2. But hey, this exponent, we could, if we wanted to, rewrite it as e to the ln of 4 all raised to the 1/2, right? And that's going to evaluate out to be 4 to the 1/2 power, or just 2. So let's see if we can find another good problem. I just realized I have a mistake in here. 4 raised to the 1/2 power is plus or minus 2. And if we think about it, this makes sense because 2 squared is going to come out to be 4, right? Plus or minus 2. That quantity squared is going to come out to be 4. The ln of 4, e raised to that is going to be 4 minus 4 is going to be 0, right? So this is plus or minus here. Do that, 4. That's another good one. 28. Is the ln of x plus the ln of x plus 8 is equal to 0. All right, so the first step here. Let's go ahead and combine these two ln's. When we do that, we're going to get the ln of x times x plus 8. This thing is equal to 0. Raise e to both sides. That's going to give us e raised to the ln of x times x plus 8 equal to e raised to the 0 coming over here now. That's going to give us x times x plus 8 is equal to 1. So x squared plus 8x equal to 1. Subtract 1 from both sides. X squared plus 8x minus 1 is equal to 0. And now we're going to use the quadratic formula to solve the rest of this problem. Because I don't see any nice factors here. We don't have 2 and 4. Yeah, there's no nice factors. So from here, we would just use the quadratic formula. And since that's going to take some time, I'm going to leave that part up to y'all. But this is how we would start on the problem. Now, having said that really quick, I want to make a point about this problem. So here we went ahead and combined the ln's, but we didn't have to do that. We could have jumped straight down to here. I'll show you what I mean. We could have said this thing implies e to the ln of x plus the ln of x plus 8 is equal to e raised to the 0. Well, this thing we can break up into 2 parts. And this thing, well, it's just going to stay 1. So we're going to get e to the ln of x times e to the ln of x plus 8 equal to 1. This is going to come out to be x. This is going to come out to be x plus 8. Same thing. So there's 2 different ways of approaching that problem. All right. I think that's enough from that problem set. Let's look at the next one. For the second part of week 9 homework, looking at number 1, we've got f of x is equal to the ln of 9x. We want to find the derivative of that thing. Well, we know from the general derivative rules of logarithms that d dx of the ln of u of x, this is going to come out to be 1 over u of x times the derivative of u of x. So if we were to decide that 9x is equal to u of x, then what we get is that f prime, or the derivative of f, is equal to 1 over 9x times the derivative of 9x, which is just 9, is equal to 1 over x. Now looking at number 2, we've got something slightly different. We've got 4 minus x to the 8th. We want to find the derivative of that. Well, that's going to come out to be 1 over 4 minus x to the 8th times the derivative of 4 minus x to the 8th. So we're going to get 1 over 4 minus x to the 8th times negative 8x to the 7th, and that's it. We could break this up a little bit, but it's not really going to help us reduce it. So let's find another problem now. That would be a good one. Yeah, let's do that. Number 3 now. This comes out to be the 5th root of 4 minus 7x. Now, before we do anything else, let's rewrite that, because that is a mess. When we rewrite it, as the ln of 4 minus 7 times x, all that raised to the 1/5 power, because that's the 5th root, right? Well, by the power properties of logarithms, we can rewrite this now as 1 over 5, the ln of 4 minus 7x. Taking the derivative of this thing is a lot easier now. The derivative is going to come out to be 1 over 5, because it's just a constant, right? We can pull that out, times 1 over 4 minus 7x times the derivative of 4 minus 7x this is just going to become -7, right? So we have 1/5 times 1 over 4 minus 7x times -7. And we can simplify this further by multiplying 5 all the way through our denominator here, right? And then multiplying our numerator by -7. When we do that, we're going to get -7 in the numerator divided by 20 minus 35x. If we wanted to, we could rewrite this as 7 over 35x minus 20. And all we'd be doing here is distributing this negative through our denominator. Cool. Let's find another problem then. That'd be a good one. So this next one is going to be number 4, and it is the ln of x to the 4th, all of this raised to the 2nd power. Now notice right away, we can pull out this 4, right? We can rewrite this as my mistake, 4 times the ln of x, that quantity squared. But we can distribute the power to the 4 and to the ln separately. To get this is 16 times the ln of x squared. All right, now notice a couple things here. We've got a few different functions going on. We can think of this as 16 times f of x of ln of x. F of x is equal to x squared. Yeah? So we can apply the chain rule here. When we do that, we're going to get 16 times the derivative of f of x let me write it out this way. Ln of x x, quantity squared. This is going to come out to be 16 times the derivative of our function, right? On ln of x times the derivative of the ln of x this is going to come out to be 1 over x. The derivative of our function is 2x, right? So this is going to be 2 times the ln of x, all times 16. So altogether, we get 32 ln of x over x. Let's check out another problem. We've got time for like 2 more, I think. Let's get those. That would be a good one. Yeah, let's go with that one. This is number 13. And we've got x times 4 raised to the x plus 4. Well, I say let's make things simpler for ourselves and rewrite this as x times e raised to the ln of 4 times x plus 4. It'll just make things easier for us. Now, when we calculate this, we're going to have to apply the product rule, right? So f prime of x is going to be e raised to the ln of 4 times x plus 4 times the derivative of x, which is just 1, plus x times the derivative of this thing. Well, this thing is going to come out to be e to the ln of 4 times x plus 4, right? Times the derivative of our exponent. Well, here that's just going to be the ln of 4, isn't it? We'll bring that down, ln of 4. Notice we've got some reductions in here now. We can pull out this exponent. When we do, we're going to get e to the ln of 4 times x plus 4. All of that times 1 plus ln of 4 times x. Well, we can go ahead and simplify this thing back down to get 4 raised to the x plus 4 times 1 plus the ln of 4 that I wanted to check out. No. No. That was all of it. I'll mix out of this. Cool. All right. So having said all that, let's move on to section 5. Go to my week 10 notes. All right. Now, while we wait for the projector to heat up, I wanted to let everybody know exam 3 will be next week. Exam 3 will be covering chapters 4 up through 5.3. Having said that, today we're going to start on chapter 5. All right. Now, to get us going on chapter 5, I thought we'd stop and think about what the derivative is, right? The derivative, we apply to some function, we get f prime, right? It tells us something about the slope. So if we're given that the derivative of some function is, say, 2x, what's that function? We wanted to go the opposite direction. What would that come out to be? So let's consider these first 2 examples. You've got a function, 3x. You've got another function, 6x squared plus 3x minus 12. We compute the derivatives. We get that f prime is equal to 3, and g prime is equal to 12x plus 3. Okay. Now let's consider 2 more functions. 3x plus 5 and 6x squared plus 3x. Their functions, or their derivatives, come out to be 3 and 12x plus 3. But that means 2 different functions have the same derivative of 3, and 2 different functions have the same derivative of 12x plus 3. So how can we undo the derivative? What does this tell us about undoing the derivative? And before I go any further, I want to point out that undoing the derivative, when we undo it, we apply what's called an antiderivative or an integral. So just some terminology, antiderivative. The antiderivative of some function is going to look like you undid the derivative plus some constant. So if some function, capital F, has a derivative, lowercase f, the antiderivative of lowercase f is going to be capital F plus c. For folks at home, if you're looking for these PowerPoints or the PDF, you can find them in chapter 3, just FYI, or exam 3, just FYI. So some points on what all this is saying, what all of this is doing, and just the anatomy of everything. We call this the integral sign. We call all of this put together the indefinite integral. what we passed through the integral, the function, that thing is called the integrand. This dx is called the differential. And provided that this is going to be true, d dx provided that this is true, then we say the integral of our function with respect to x is equal to f of x plus c. And this is the antiderivative of lowercase f. So again, just reiterating the definition of all of this. So some points on notation. The integral of 2 with respect to x is equal to 2x plus c. The integral of 3x squared with respect to x is going to be x cubed plus c. The integral of 4t with respect to t is going to be 2t squared plus c. Now let's check this out for a quick second. Let's try to undo these integrals, these antiderivatives. Applying the derivative to 2x plus c, this is going to come out to be 2. Well, the derivative of a constant is 0, so it's just 2. Doing the same thing now to x cubed plus c. Well, the derivative of a constant is 0. The derivative of x to the third is going to be 3x squared. The derivative with respect to t of 2t squared plus c is going to come out to be just 4t. So they seem to be undoing each other, right? And that's because they are. They are opposite operations of each other. The integral undoes the antiderivative, undoes the derivative, and the derivative undoes the antiderivative. So having made that point, they just undo each other. They're inverse operations. So, some basic integral rules. The integral of a constant with respect to x is going to be that constant k times x plus some other constant c. The integral of k times a function, where k is some constant, is going to be equal to k times the integral of that function. The integral of two functions added or subtracted from each other will be the integral of one function plus or minus accordingly the integral of the other function. And then we have what's called the simple power rule, which is really just the opposite of the power rule of derivatives, right? So in the beginning of the semester, we had learned that the derivative of x to the n is equal to n times x to the n minus 1 Undoing it now, we're going to get that the integral of x to the n is going to be 1 over n plus 1 times x to the n plus 1 plus c. But there's a catch. The catch is that undoing the derivative, we have to have that n is not equal to -1. And this kind of makes some sense, right? Because when we get to just x, right? When we take the derivative, of something like k times x, this is just going to come out to be k. When we take the derivative of k, this is just going to come out to be 0. And we can't go beyond that. We just keep getting 0 as we keep adding derivatives on, right? So there's no way that a derivative using the power rule can ever be applied to get something out that's -1, right? So we have to be careful when we apply the inverse of it, that we know not to apply the simple power rule whenever n is equal to -1. So really quick, I'm going to let y'all, well, I don't have time to do that. I'm going to go ahead and call it at this. We're going to pick up from here tomorrow, Thursday. Having said that, again, the exam for exam 3 will be next week. It will cover chapters 4 to 5.3, and we'll finish 5.3 next class, in theory. In theory, we'll get that far. If not next class, it'll certainly be next Tuesday. Having said that, if y'all have any questions, I'll stick around.